Christos is a global segment coordinator at TÜV Rheinland, and Christos is going to speak on from lab measurements to field evaluation, LCOE assessment of BCPV modules. Christos, the floor is yours.
Thank you, Shravan, for the kind introduction. Indeed, it is my pleasure to give a talk today. Let me share. Can you see my screen now?
Yes.
Lovely. Let me go in presentation mode. Okay, so thank you so much for the kind introduction. Today I'll be giving a talk on looking beyond the nameplate, quantifying true module value using LCOE as a metric. It is essentially a comparative study between two modules. One was a Back Contact technology and the other was a TOPCon technology that we have been contracted to perform by LONG-G. Please give me a second. I would like to get rid of this top bar over here. No, I don't think I can get rid of it. Okay, there it is. Good. So a couple of things about TÜV Rheinland. So TÜV Rheinland, we take pride about the reputation that we have in solar. We have 40 years of experience in PV. We are active in more than 500 locations in almost 60 countries around the world. Worldwide, we have over 250 experts working for solar. We are in power plant inspection since 1990. We operate over 9,000 square meters of lab testing area, and we are also, of course, known for being a third party, being independent and impartial. Right, so let me move on to the next slide. So what I have for the agenda for today is, first of all, I will discuss with you about the limitations of simple metrics, such as just looking dollar per watt peak. Then we'll see why using levelized cost of energy, or LCOE, if you like, is a better metric. I will introduce you to the LCOE assessment methodology that we have to do the evaluation that we have done. And then we will show you a case study comparing a TOPCon model with a Back Contact model and conclude. So what is the problem? If you look into the dollar per watt peak, may actually not reveal the whole story. So traditionally, modules are purchased based on upfront costs, dollar per watt peak, which ignores critical performance factors that impact lifetime energy yield and profitability. So there are key factors which are being ignored by this approach. Many things such as degradation rates, temperature coefficients, low light performance, bifacial gains are not taken into account. And there are also many more things. If you look at the LCOE, which I think you can understand it as a golden standard for energy cost evaluation. So LCOE expresses the average net present cost of electricity generation for a plant over its lifetime. So it's total lifetime cost divided by the total lifetime energy production, if you like maths. And what it tells you what is the minimum price at which the energy must be sold for the project to break even. So if you have a lower LCOE, that means that you have a more profitable project and lower risks. Overall, it combines capital expenditure, operational expenditure, if you like CapEx and OpEx, but also financial factors. But most importantly, it also takes into account the energy yield as a comparison metric, which gives a far better, more reliable estimates about the profitability of the project. I would like to take a look on what approach we have done to evaluate the LCOE. So basically, we have utilized lab testing, which gave us access to comprehensively characterizing module performance parameters such as the STC power, temperature coefficient, spectral response, low light performance, IEM, LAD, and also NMOT. We combine this with field testing, which we use to validate the performance against actual weather data of varied irradiance, temperature, and spectrum, give some better estimates about the LID losses of the module, but also provide an estimate for the first year degradation of the module in the field. The case study that I would like to present consists of two modules. One is TOPCon, and call it Model A, and Model B is a Back Contact module. We have tested key parameters such as the STC power, temperature coefficients, low light performance, incident, excuse me, incident angle modifier, and also NMOT and the performance under shading. We have also taken some assumptions related to the size, location, CAPEX, and OPEX, which allow us to provide an LCOE estimate. So for the assumptions, the data have been provided by the datasets of the module or by LongG. So let's take a look at the two samples that we'll be comparing. They have very similar module dimensions, 2.4 by 1.1, both of them. There is a significant difference in the nameplate power. So here what I show you is the nameplate power, not the measurements that we have done. The back contact module significantly delivers more power, and that was also verified by our measurements at STC. Delivers significantly more higher power because inherently the back contact module does not have any shading from front metallization that TOPCon modules cannot avoid, right? So it enjoys higher core conversion efficiency. So in this specific model, we've had a 24.4% efficient module. That was, I would say, almost a ridiculous look to me. I thought it was a cell efficiency, and then I asked our engineers, "Are you sure that this is the correct data that you're working with?" And they verified that this is actually module efficiency here that I state 24.4%. Ridiculously high, if you ask my opinion. The TOPCon module also had a very high efficiency, was close to 24%, 23.7%. So I would say the solar industry have come a long way. Me being a guy that was used to measure PERC modules or aluminum back surface cells, that the efficiencies were above 20%, and we were thinking that PV modules will deliver significant power at this age. Looking at the progress of the solar industry as a whole, these are very, very impressive results for me. Anyway, so the temperature coefficients were similar. We've seen that back contact enjoys a slightly lesser temperature coefficient. We will look at it a bit more later. Bifaciality here, the advantage is on the TOPCon. It enjoys a slightly higher bifaciality, but as Alex has mentioned, you should not only compare the bifaciality, but the shear output of the module in terms of wattage. So the back contact module will always deliver higher, more watts in any condition. We have taken into account some assumptions which came from the data sheet. So for the first year degradation, that was also able to verify this by measurements that we have conducted in the field. The dataset states for both of them 1%. I think is reasonable. And they also LongG here also has a slightly lower guaranteed annual power degradation rate than the TOPCon module. This I'm not able to verify. This actually the difference is very, very small. It will translate into some small gains in the LCOE calculation. I would like also to repeat that I'm not able to verify the annual power degradation that the module have, and I take here an assumption that comes from datasets. Right, so let's jump into the temperature coefficients. We were able to characterize the temperature coefficient of the modules using the procedure which is detailed in IEC 60891. So you basically vary the temperature between 20 and 65 degrees and measure the temperature coefficient. I will only talk about the temperature coefficient of Vmax because I think this is most relevant for the audience here that we have today. So we see that the temperature coefficient of Pmax is a little bit lower on the back contact module compared to TOPCon module, minus 0.27% per Celsius degree, comparing to minus 29% per Celsius degree that the TOPCon had, a tiny advantage. Generally speaking, I compare this with my experience with the old modules that had minus 45% per Kelvin Celsius degree. So I see that we have made a big progress. 20 years ago, the temperature coefficients were different. So the manufacturers are able to suppress the temperature coefficient of the modules. And these modules looked almost temperature insensitive to me. I would say they approached heterojunction levels, that they had super small temperature coefficients. Right, IAM. We also compare the IAM between the back contact module and the TOPCon module. The procedure that we followed was in accordance with 61853-2. So basically, when you conduct these measurements at low angles of incidence, the total measurement uncertainty, which is the graph I'm showing you here on the right, is driven by STC factors. As the angle of incidence increases, it's driven by factors related to the measurement of angle itself and increases significantly. Nevertheless, here we have seen that the back contact module has a far superior performance compared to the TOPCon. So at 75 degrees, the difference materialized close to 5%, which is, I would say, huge. However, I would like to drag your attention on this. I don't think that the back contact technology has superior IM than the TOPCon. What drives the IM performance is the glass and the light management schemes that you have in the module. So maybe I think here you have like a better glass with superior anti-reflective coating, which also resulted in a far superior IM performance. A lot of people, also I would say this generally speaking, they compare back contact modules and TOPCon modules. Back contact and TOPCon is just a cell technology, right? It doesn't say anything about what is the encapsulation of the module, which is the most critical part also when it goes to reliability. We also conducted field measurements. I don't have the time to go through all of the things that we have done, but I will just stick to a couple of things that I think are important. NMOT, we actually characterize the coefficients that can provide the NMOT of the PV module. NMOT, for those who do not know, stands for nominal module operating temperature and represents a typical, let's say, temperature of a module under real outdoor conditions. A lower NMOT would translate into reduced thermal losses and a higher energy yield. Basically, it means that the module can cool down more efficiently. We have seen that the back model B had marginally lower NMOT than the TOPCon model A, about half degree per Celsius, about a half degree Celsius. I don't expect that this would have like a significant effect on the energy yield, but it will also materialize into a small advantage of the back contact technology compared to TOPCon. Another thing that we did, we studied the shading resistance of the PV modules. For this, we employed 2PFG 2926, which is an internal standard of TÜV Rheinland. And we used as a metric a rev, which is used to quantitatively evaluate PV modules' energy loss. There's also input factor in PVCs. So here, if you have a higher a reverse value, would indicate that you have a better performance under shading. So here we have seen that the back contact module has significantly higher a reverse, which results in significantly lesser shading losses than the TOPCon module. So this is also inherent advantage of all back contact technologies. Essentially, they don't actually have a bypass diode in each of the cells, but the technology itself acts like this. So essentially, it's like you have a diode at the back of each cell. So when you shade the module can circumvent the current flow around the self itself by tunneling. And this also saves a lot of energy when the modules are shaded. It's not like it will save 100% of the energy, but there is no comparison because before compare like back contact cells with conventional technologies. The back contact cells will always provide lesser shading losses. Right, let's now move ahead. And in this example, we have assumed a site which is in the United Kingdom, southern England, at Southampton. The insolation at Southampton is approximately 1,120 kilowatt hours per square meters over a year. And the temperature varies between -12 degrees to 36 degrees. And we use environmental conditions that were documented in Methanon database. We used 3 different installation scenarios. Scenario 1, we installed the TOPCon model A. And in the installation, we achieved 18.5 installed peak power. Then we used the back contact model B and tried to reach as close as possible to this value here that we reach with the TOPCon model. So in this specific example, we are able to reach 18.6, which makes it, let's say, almost comparable. So here we have same DC power installed. And we also use the third scenario where it didn't go by power, but we say, well, how much area have we used installing a TOPCon module? And I'm going to use the same area and install as many modules as they fit. So in these 3 scenarios, we used a different, in the third scenario, of course, we were able to reach a higher peak power because the modules have higher conversion efficiency. So the number of modules that in the first example and third example are the same, close to 30,000. And the modules that we used in the second scenario were a bit less, 500,000 modules. We used the same number of inverters. We used, fixed installation at the tilt facing south at 20 degrees. And these were the parameters, the 3 cases that we have examined. So we have conducted an energy yield simulations over a 30-year lifetime of the PV modules. And we have seen that if we compare the energy yield output on the first year, the TOPCon modules delivers almost 20 megawatt hours, while the back contact module B, which had the same installed DC power, deliver approximately similar energy output, 1% higher though, 20.3 megawatt hours. And if we're looking at the same area, it was also here, there was a significant difference. The modules, the third case delivered almost 20.8 megawatt hours. If we make a projection to a 30 years lifetime, taking into consideration factors such as the guaranteed degradation of the manufacturers have provided, the total energy yield further, the difference between TOPCon and back contact modules further increased by 1%. So the difference exceeded 2% when we used the same installed DC power. And when you use the same area, the difference exceeded 5%. So this information would materialize as a small difference of the back contact technology comparing to TOPCon. We're looking at the energy loss, so which were the factors that have driven these differences. First of all, we stop at IAM. We have seen that the back contact module that we have studied indeed had a superior IAM performance. So basically, when you have diffuse light, such as the case of Southampton in England, that is a relatively cloudy location, these gains would maximize. There was also a very small advantage when it goes to the temperature losses, that we have seen that the TOPCon module had like higher losses comparing to both back contact scenarios that we have installed back contact modules. And there was also a small but quantifiable advantage when it goes to shading. So these were the factors that have driven the difference in the energy yield loss of these PV modules in the first year of the operation. Now going back to the LCOE, if you remember, we said that we would like to use LCOE as a metric to compare the PV modules. So LCOE is the average net cost of electricity generation for a power plant over its lifetime. It takes into account the CapEx, the capital expenses, OpEx, operation and maintenance expenses. Also takes into account the energy yield, the power generation. And you also have to consider several financial factors such as tax rate, depreciation, real discount rate, and how many years you assume that this module will last in the field. So both of these modules in the dataset, I think the manufacturers promised 30 years. So we have done the analysis on the LCOE, but also energy yield, what I've shown you before, for 30 years. Let's move on. So here we have also taken into account some information that was provided by LONGi about the CapEx and the OpEx. I have to say I was a bit surprised when I saw that. On top of my head, I thought that back contact modules will definitely deliver more power. There is no doubt about this, but I thought were a little bit more expensive. So the data that we have been provided by LONGi suggested that the CapEx is almost the same with TOPCon modules. Actually, they even gave a small advantage to the back contact technology for the capital expenditure. So when the total CapEx that we have for the TOPCon module was 0.7 euros per watt peak, and we're looking at the case where we installed the same DC power, it was almost the same, 0.697 euros per watt peak. And it was a significant advantage where we installed modules the same area as we occupied with TOPCon modules, was 0.682 euros per watt peak, almost 2.5% lesser. Anyway, I mean, we have, of course, taken the data that we have been provided into account. Maybe I also like to take some distances for them. I think it's probably reasonable to assume that they have similar CapEx and OpEx. So, and then taking all these factors into account, we calculated the LCOE. So LCOE advantage translates directly to higher project profitability and a stronger case for financing. So we have seen that the back contact technology case B and case C have lower LCOE, especially the case C, where we have the same installation area, has 3% lower LCOE comparing to the LCOE that the TOPCon module delivered. And also looking into the internal rate of return, which basically quantifies the return of the investment, which gives a percentage of gain or loss to an investment relative to its initial cost. So we see here that in terms of the IRR, there is a 2.5% difference between the back contact module that is limited by the DC power capacity. It's the same, the DC power capacity with TOPCon installation, 2.5% difference in terms of the IRR. And there is almost 4.5% difference in the IRR when we use the same installation area. So, of course, not a big surprise that the LCOE is lower for a back contact system. I thought that the back contact modules tend to be a little bit more expensive, but taking into account recent information from LONGi that they were able to suppress the cost to the levels of TOPCon modules, of course, they would have an advantage. To conclude, the accurate assessments of PV modules requires examination of several of the performance characteristics, such as low irradiance, temperature coefficient, IAM, shading resistance, and degradation rate. In this specific example, two module types, one TOPCon and another back contact solar cell technology, have been compared. The results showed a relatively small but quantifiable advantage of the back contact module type in terms of energy yield and LCOE, I would like to add. I would also like to draw your attention that these results may not be easily generalized. We have to examine each module case by case. Therefore, these results should be also understood with caution. So accurate assessment of energy yield and LCOE of PV modules requires a case-by-case evaluation of the module types of interest. And I would like to close my talk. I would like to say a couple of things. If you're a developer or an investor, we can provide project-specific LCOE assessment for your modules. If you're a manufacturer, we can prove your superior LCOE to gain a competitive edge in tenders in case you want to compare with specific module type that you would like to investigate. And overall, we offer technology-specific LCOE benchmarking, also pre-investment bankability studies, and energy yield prediction and performance ratio validation. So I would like to thank my colleagues, Mr. Mark Yuan, Mr. Chesel Xie, and Dr. Mengdi Liu, in the help of making this presentation and also reviewing this work as well. So I would like to thank you very much for your attention.